So now we're going to start with the next chapter and the new functional group that we're going to be looking at, and we're going to be studying for the next couple weeks, or if not more, if not longer, are the carboxylic acids, and then later we'll go into the carboxylic acid derivatives. And so if you remember from this last semester, a carboxylic acid has a generic form of R, C double bond O, which is a carbonyl or acyl group, OH. This is not like a typical alcohol or a ketone with an alcohol on it. We're going to see that it has very distinctive functional properties. So it's actually quite easy to follow the IUPAC nomenclature rules. So first of all, carboxylic acids, since it has that carbon is making 3 bonds to oxygen groups, they take priority over alcohols, ketones, and aldehydes, as well as ethers. Okay, so what you do is you want to find the longest chain containing the carboxylic acid group, just like what we've done in the past. That becomes the root. Make sure that you use the correct numbering system, like meth equals 1 carbon, eth is 2, prop is 3, bute is 4, so on and so forth. Okay? You would name that alkyl chain, but you want to drop that terminal E, like what we've done in the past with alcohols, for example. And you add the following ending. The ending is oic acid. Okay, so let's do some examples. Okay, if we first look at the compound on the left, we want to see it has 1 carbon, and so that would be called methane in particular. But we drop that terminal E, we add oic acid. The one on the right would have 2 carbons, so it becomes ethane, but we drop the terminal E and add oic acid. Now both of these actually also have IUPAC acceptable names that are common names. So for example, if you remember, a single aldehyde group was called formaldehyde. This becomes formic acid. And the acet group, like acetaldehyde, this is acetic acid. I do expect you to know both of those common names. Let's do another example. This time I'll draw one. Okay, I didn't draw it well, but that's all right. So we have a benzene group, and so this would become benzene carboxylic acid. However, I will tell you right now, that is not. It also has a common name, one that you've actually already memorized in the past. That is IUPAC acceptable. Instead of benzene carboxylic acid, is more commonly called benzoic acid. Okay, let's do another example. Okay, this time we'll make it a little bit more challenging. I will give you a moment to look at this compound and to come up with the IUPAC acceptable name for it. If you need additional time, feel free to push pause. So first we need to look at the longest carbon-containing chain that has the carboxylic acid. And so we could either have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. And so it's going to be 8. And so that's going to be the root, which would be octane, but we drop that E and we add the oic acid. So we have octanoic acid as the root. Now we have to name all of the functional groups hanging off. We have this functional group, we have this functional group. I'm going to do whichever one comes last in alphabetical order. The one on the left is the ethyl group because it has 2 carbons. The one on the right is a hydroxyl group because it's the alcohol, but the alcohol takes backseat to the higher priority carboxylic acid. So since the alcohol group starts with an H, it's going to be the group that's closest to the root word, so it's hydroxy. I'll also accept hydroxyl, because many times it's called that. Okay, and we have to give it the locant. And remember, the numbering starts with the highest priority group, which would be the carboxylic acid. So that is carbon number 1. So we have 1, 2, 3, 4, 5, 6. So that becomes the locant. And then finally we have the ethyl group. And its locant, 1, 2, 3, 4, is a 4. So we have 4 ethyl, 6 hydroxyoctanoic acid. So if we think about it, let's first consider boiling point. If we just look at comparable alkanes, so let's say that they're about the same size, and we're talking about the same size and surface area, versus the alcohol, versus the similar sized aldehyde or ketone, versus the carboxylic acid. All things considered, if the surface area is comparable here, how will these rate with respect to the lowest boiling point to the highest boiling point? When we talk about boiling points, we're talking about an intermolecular bonding. So the lowest is going to be the alkane. And the type of bonding intermolecularly here is only the van der Waals forces, or induced dipole. The second lowest would be the aldehydes and ketones, if the surface area is comparable. The reason being is they cannot fully reciprocate a hydrogen bonding, so they only have dipole-dipole interactions. Third, or the second highest, would be the alcohol, because the alcohol can do the alcohol can do hydrogen bonding. And finally, the carboxylic acid, all things considered, would have the highest boiling point. And so if you wanted just an example, if we just look at 2-butanol versus propanoic acid, surface area is about the same. The boiling point here for 2-butanol is 99 degrees Celsius. Very similar to that of water. Propanoic acid has a boiling point of 141 degrees Celsius because not only can it do hydrogen bonding, but we're going to see that due to the ionization effect that you're going to be able to do this unique type of hydrogen bonding arrangement with respect to the carboxylic acid. So what I mean by that is if we look at it this way. Just a second, let me put in a carboxylic acid. So we have a hydrogen bond donor and a hydrogen bond acceptor. Alright? So what happens if there's another one of these carboxylic acids nearby? What kind of bonding can occur between these two? So now we have another hydrogen bond donor and hydrogen bond acceptor. So between these two, we can actually get this unique type of hydrogen bond formation. Because of that, it becomes much more difficult to break these two bonds. You have to put more energy into it to break the two bonds apart in order for it to escape from the liquid phase to the gas phase. The next question, that many times that we talk about, is water solubility. What kind of interactions are there in a carboxylic acid? So if we take something like acetic acid, is it soluble in water? And the answer is yes, it is. And the reason being is because, again, it's highly, highly polar. In fact, we're going to find out it's ionic, okay? And so something like acetic acid or formic acid or propanoic acid, they're going to be water soluble. However, here, like many things in life, size matters. So what happens if you have something like this, where the overwhelming surface area of the molecule is hydrophobic? If we look, we have this hugely hydrophobic region with a relatively small hydrophilic region. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, because this is decanoic acid. So there's 10 carbons, but only one of those carbons has the carboxylic acid. And so because of that, the overwhelming hydrophobic portion would make this much less water soluble. And in particular, this is called something that's amphipathic. Okay? And it can form something called micelles. The reason being, and now I'm just going to draw it like these. Whoops. You can have these hydrophobic regions that will want to exclude water. And then they have these hydrophilic, negatively charged head groups. That's where the carboxylic acids would be. Due to this unique property, you can use carboxylic acids and carboxylic acid derivatives, especially the carboxylic acids, in order to be a type of detergent where the hydrophobic oil or what have you would get stuck on the inside of the hydrophobic interior of this micelle, and then you could have the hydrophilic portion being exposed to the water. Which that leads us into the third and the overwhelming property with respect to the carboxylic acid. And that's the fact that it is an acid, and so is the acidity. And I just want to look at one specific example, because this is something that you do back in Gen Chem. So if we have ethanoic, or also called acetic acid, and you place that in water, what does an acid do? What is the rule of thumb with respect to acids? They protonate. And so we're going to have the electrons on the water swipe, bang, sound effects optional, take off the proton, and the two electrons that were held between the oxygen and the hydrogen, are going to go towards the delta plus portion of the carbon. Something has to break or leave, and we can break the double bond. This is definitely fast and reversible, so it's constantly happening. And we now have this anion, plus the acid, the hydronium ion from the water. Okay? And I do expect you to know how to name the conjugate base of these acids. Okay? So, to name this one, what you do is you would name the acid, carboxylic acid. You drop the ic acid part and just add ate, A-T-E, because that indicates that it is an anion. So, for example, this was acetic acid, so this becomes acetate. Okay, so this is the acetate compound, or anion. Okay, so let's do one other example. I'm just going to draw one now. And now let's name that. Okay, so we get a different color for the highlighter. We have to count 1, 2, 3, 4, 5. So that would be pentoic acid. Okay. We drop the ic acid. So it becomes pentoate. And of course, there's going to be a positive cation along to balance this charge. So we would just, for example, if it was sodium, this would become sodium pentoate. If you have benzoic acid, it could become sodium benzoate, or lithium benzoate, or magnesium benzoate, so on and so forth. Okay? So what is it about these carboxylates that make them so good that these carboxylic acids are good acids? They're not going to be strong acids where they're 100% dissociated in water, but they are going to be good acids. And so let's just go back to our simplest, or one of the more simple ones. And I'm not going to draw the hydronium ion just for clarity's sake. So we have acetic acid becoming acetate. And if you notice, in the conjugate base of acetate, we have resonance. And if you think back to GenChem, so here let me change and I'll show you how the resonance occurs. You have these electrons moving down, these breaking, and so now we have that. And if you think back to GenChem, any time that you have resonance possible, for the most part, then we're going to increase the stability. And so since the conjugate base is more stable, it's going to cause the equilibrium to shift towards the formation of the conjugate base. That's the reason why acetic acid is a good acid and becomes acetate. And the pKa is roughly, 4.7? Roughly about 4.7. Hopefully this helps you in learning how to name the carboxylic acids, naming their carboxylate, the conjugate base of it, and also the physical properties of carboxylic acids.